طيب بسم الله الرحمن الرحيم. So we're still talking about the Bluetooth standard 802.15.1, and we discussed this layer stack last time, and we said that the Bluetooth radio layer corresponds to the physical layer, and it uses the carrier frequency 2.4 gigahertz, and it has 79 different hop frequencies or frequency subchannels that it hops from one of these frequency ranges with a speed of up to 1600 hops per second. So technically at every transmission you can switch from one frequency to another. Okay? Of course the hopping itself is random. And we said that the hopping uses fast FHSS اللي هو frequency hopping spread spectrum, and in the physical layer we use GFSK or Gaussian frequency shift keying as one modulation scheme. So there is no adaptive burst profile like the case of the metropolitan standards. So here we have one communication scheme. As we will see later is that we do have different forward error correction schemes as part of Bluetooth, but the modulation scheme is fixed. So this is for the radio layer. The baseband or the link controller, we will talk about it today, and it basically uses TDD or time division duplexing and TDMA. Okay, so time division duplexing is for full duplex communication. So basically one time slot for sending from the master to one of the slaves, and the other direction uses another time slot for sending from the slave to the master, one of the slaves to the master. Okay, so it's TDD for bidirectional communication, and TDMA, which means that each slave or each node sends in the uplink in the time slots that's assigned to it, so there's no collision. And we talked briefly about the fact that because Bluetooth was actually designed for both data and voice communication, okay, unlike all the previous standards that we talked about, as we said, Wi-Fi is originally designed for data, and that actually dictated the fact that we use Cisma CA for channel access, and Metropolitan Area Networks was designed originally for voice, and that's why it adopted the TDM or TDMA to provide some guaranteed quality of service, which is one of the requirements for having high quality voice communication. Right here we have a mix of both. We have voice communication, and we need to provide also data support or data communication. Therefore, the TDD, TDMA will actually enable us to provide both. How? Well, basically for data communication we use time slots, and we can assign these time slots to provide both differentiated services or guaranteed quality of service, guaranteed delay, guaranteed bandwidth, and so on if needed. For voice, however, as we will see later, for voice communication, so this direction or this path, we need guaranteed quality of service. So we need to provide guarantees on the bandwidth or the throughput to be able to have high quality voice communication. So that's why the standard provides circuit switching like connection. So in circuit switching, as we said, we have to establish a connection first, and during the connection establishment we need to provide all the reservation for the resources, in which case we can provide guaranteed quality of service. Right? So before we start communication, we need to establish the connection. During the connection establishment, we can then dictate how many time slots we need in the MAC layer and pre-assign these time slots before beginning to communicate. So this way we can sort of estimate exactly how many time slots we need for this voice communication to be high quality. And reserve all these time slots beforehand to this voice communication. And the rest of the time slots can be allocated dynamically to the data communication. Okay, so this is a very important concept. So how can we provide circuit switching light communication, okay, using the TDD TDMA? Okay, so the answer to that is that before we start communication, we do connection establishment. Once we do connection establishment, this is connection-oriented type of communication. During the connection establishment, we pre-allocate fixed number of time slots to this connection. So these time slots are pre-allocated to this connection. So this way we can guarantee the resources, and in which case we can provide guaranteed quality of service. Okay? So this is the case for this direction. For this direction, we don't have to do this for data communication. We don't have to do this beforehand, I mean, but we can do that dynamically at any point in time. Okay? And we'll talk about this. We call it asynchronous connectionless communication. Okay? So this is synchronous and connection oriented, and this is asynchronous connectionless. Okay? So all of this is facilitated by the baseband channel access, which is a TDD TDMA. So the link manager is responsible for setting up and controlling the link between the master and one of the slaves. Okay? So this connection will have some packets going from the master to one of the slaves and the other way around, from the slave to the master. Okay? So to set up a new connection, you need to call some APIs from this layer to set up the connection. While you are setting up the connection, you need to define whether this is for voice or for data communication. Whether you need to pre-allocate the time slots from the beginning, or you don't have to establish any connection, in which case there is no actual connection context in the link manager for this particular connection. Or you can stop the communication or tear down the connection at any point in time. The host control interface is to interact with the lower layers, controlling all the parameters of the lower layers, including the connections, getting some information about how many connections are currently running, and so on. And as we said before, this corresponds to the management entity in the metropolitan standards, or 802.16.1.
As a link manager, at this stage we would know if the slave and like the connection between the slave and the master is for data or voice, right?
Right. The link layer adaptation protocol, or connection and adaptation protocol, this is L2 CAP. The L2 CAP, as we said before, is responsible for adapting or customizing the high-level services to the lower layers, MAC layer and physical layer. In which case, because again Bluetooth, unlike the metropolitan area networks, Bluetooth is used for diverse set of services. So you can use a Bluetooth device as a mouse, right? In which case, you need to emulate communication similar to the serial communication, right? So you can use a keyboard or a mouse. Keyboard or a mouse uses serial communication, right? So Bluetooth provides the RF COM, which is an emulation of serial communication over wireless, which is what we call RF COM. Okay? Or you can use a human interface device. Other human interface device, you can use Bluetooth, like EEG headsets or something like this. So you can use a different service called HID. So these are application level services, okay, that the Bluetooth device makes it available for you. So one Bluetooth device acts as a mouse, as a keyboard, as a human interface device, or as data communication, TCP/IP, or as telephony. So when we have like a headset or something, or any device that deals with voice communication, and you can send back and forth some signals related to how to start a new voice communication, how to stop conversation, and so on. So this is a telephony control service. So these diverse set of services, okay, requires different, or they have different requirements in terms of what they require from the lower layers, in terms of how many time slots and how the packets themselves look like, what is the rate required, and so on. So depending on each service, you may have different requirements. Okay, so we did not have this diversity in the metropolitan area networks, and that's why for wireless personal area standards, they usually talk about application level profiles. So they provide application level profiles for each application, or for each set of services. Similarly, for Zigbee, for example, there is an application profile for healthcare. There is an application profile for different categories of application. Okay. So for Wi-Fi and metropolitan area network, they don't do that. So the standards do not include any application level profiles per se. So they leave that up to the vendors. But in personal area networks, usually they include it in the standard. Okay, so that's a differentiation. And that's because of the fact that, again, the personal area network standards, they are designed for both voice communication and data communication, and therefore they can provide diverse set of services. Okay, Kida? So these are the different layers, and this is the description for basically a high-level description of what is the function of each layer, which is what we talked about. So there is a service discovery protocol, which we didn't talk about. Service discovery protocol is the one that you interact with initially in order to know what kind of services are available on this Bluetooth device. Okay? So this is the one that tells you you can use this device as a mouse, or you can use this device as a human interface device. Okay? Or this device actually provides some telephony control services. Okay? So the service discovery protocol, you usually communicate with the SDP module first to know what services does this device have in terms of Bluetooth. Okay? Because there might be some devices that provide multiple services or different set of services, in which case you need to discover what services are there. And that's what happens on Windows. So I need to discover if there are some printers out there that works using Bluetooth, or any mouse, or any projectors that use Bluetooth. Okay? So what you do is that this service discovery protocol will will send some broadcast messages of what services are available, okay, which any Bluetooth device can now read and get some idea about the set of services that are available, and then you can start pairing with that device. So you pair with that device to use one of these available services. So SDP is what makes all the other services exposed to you, so you can use one of or more of these services.
There is no such corresponding protocol in wireless communication?
Yes, and wireless communication, كل ده wireless communication. You mean like in metropolitan?
Yeah.
Yes. As I said, these standards, they leave this part of the specs to the vendor. They don't actually specify anything in there. Usually that's what happens. But for Bluetooth, And that's a habit actually that I noticed personally throughout my experience. Yani in the personal area, in wireless personal area network standards, most of the standards, they include some high-level application profiles in the standard. Okay, which is not the case in other types of standards for metropolitan area networks and for local area networks. Okay, so that's the high-level description of the function of each layer. So now we can dig into each of these layers to understand how they work in more details. So basically, as we said before, a piconet is composed of one master and up to 7 slaves. When we say up to 7 slaves, we mean up to 7 active slaves, which means that these slaves are communicating at the moment. Okay, so these gray ones, these are active slaves, and you can have up to 7 only. With the master, it becomes 8. And this is dictated in the frame that you will see the address. The address that you can identify a certain node is actually 3 bits only, which gives you from 0 to 7. Of course, 0 is reserved, so you have from 1 to 7. So the master can send to one of the slaves using this address bit. You can have up to 200 other nodes, but they are in park mode. They call it park mode. They are not communicating. They are not active. They are part of the piconet. Okay, in which case they are paired with the master. Okay, so they are virtually part of the piconet. However, they are not communicating anything. Okay, and you can have the standard actually has a limit of like 200 devices, but they are not communicating, so they are useless. Or in a standby mode. In a standby mode, this means that this device is not paired with anything, is not actually part of any piconet. Okay, so it's not part of any piconet. So these are the 3 modes that we have for the slaves. Okay. A node can be in the standalone, or sorry, the SB mode, in which case it's not a master node nor a slave node. So it can actually be in a standby mode, which means that it's not connected to any piconet, and it's not a master and it's not a slave.
The other node can see the standby node?
No, it's the other way around. Usually what happens is that the standby nodes, first what they do is that before they have communication, first they try to discover what are the available piconets that are there. Okay? And it tries to receive some beacon messages from the existing piconets, okay, and based on that, it knows what are the Bluetooth networks that are available, and then it pairs with one of them. When it pairs with one of them, then it's part of the piconet. Now it needs to have communication in order to be in active mode. All right. So once you pair, you are in the park mode and you are not doing any communication. Once you start connecting some services, then you are in active mode. And you can have up to 7 slaves in active mode. Waha? Okay. So that's the channel access mechanism. So the channel access mechanism here is TDD. Okay. In the first time slot, it's always, in all even time slots, it's always master sending to one of the slaves. Okay? In one-to-one or one-to-many communication. Okay? In the odd time slots, it's one of the slaves communicating with the master node. And as we said, the communication always goes through the master node. Okay? So even if two slaves are communicating together, they have to go through the master node in a two-hop communication. So what is the difference between this and the TDMA in the case of 802.16.1? It uses CMA as well, right? Okay. What is the main difference here? In the 802.16.1, we divided the frame into two subframes in TDD, right? Here, all the time slots are mixed together. There's no actual subframe boundary. So each time slot is in one direction. So one time slot, the even time slots are from the master to one of the slaves, and the odd time slots are from the slaves to the master. So it's like the two subframes are mixed together in odd and even time slots. Okay? But in 802.16.1, we actually subdivided the frame into two subframes. Each subframe has multiple time slots, and these multiple time slots are in one direction. Right? But here, all the time slots are mingled, are actually interleaved together. So this is actually the main difference. But it's logically it's the same. But it does affect a little bit how you provide quality of service guarantees. Because in order to provide quality of service guarantees, you need to estimate what would be the delay if I assign the time slots in a certain way. So whether these time slots are mixed together or they are in a sub frame, it affects slightly how you calculate the delay and so on and so forth. But for us, they are the same. Okay? Okay. Anything unclear here? So this is actually how TDD, TDMA works in Bluetooth, which is slightly different from 802.16.1. All right, so this is the frame format. And Bluetooth actually defines three types of frames: the 1-slot frame, the 3-slot frame, and the 5-slot frame. So the TDD, TDMA that we had in the previous slide, you have each time slot, okay, correspond to 1-slot frame. Okay, one data frame. There is a possibility that you can use 3 time slots and use all the 3 time slots as one frame. So the standard actually allows that, and the only benefit for this is that, of course, this header and the access code, these are overheads, right? So if you have a 3-slot frame, so you need to have one header for 2 time slots. So the overhead is lower, is less. Similarly, if you use 5-slot frame. But remember, if you have 1-slot frame, you are allowed to hop from one frequency to another at each single frame. And we have up to 1,600 of these frames per second. Okay? So in which case, you can hop 1,600 times per second from one frequency to another in the physical layer. Of course, if you have 3-slot frame, in that case, the frequency will drop. So you're not, of course, expecting that we hop during the frame transmission. So the frame transmission is transmitted as one unit on one frequency. So if you have 3-slot frame, so you have 3 slots with the same frequency, which means that the hopping frequency is dropped. ماشي? Or if you have 5-slot frame, then you hop every 5 slots, not every slot. Okay? So that's so this is basically the frame format. So the access code is used to provide synchronization at the different time slots. It's what we had called before in 455 the preamble, and the preamble is usually used to synchronize the transmission at the beginning of each time slot. Okay, and the header is then divided into these fields. The first field, as we said, you have 3 bits only. to address one of the 7 slaves. Of course, when one of the slaves addresses the master does not have to be identified in that case because it's 1. There is a type field, and the type field actually corresponds to different data types from the application layer data. So you can have different data types coming from the application, whether this is coming from HID application or TCS application or a mouse or whatever. So you can provide different data types. And similar to TCP flow control, these are flags that are used in the exact same way like TCP. So this flag is for flow control. This flag is for acknowledgement, or so if this flag is 1, this is an acknowledgement frame. Because actually in the MAC layer, the Bluetooth uses some kind of flow control and forward error correction. So this is the forward error correction bits. And in fact, this number of bits can be allocated differently to indicate different forward error correction schemes. So there are multiple of these defined in the profile. So you can define the HEC field in a bunch of different ways to provide different schemes for forward error correction. Based on that, you can provide some error correction for different types of errors, okay, to correspond to the different services that you have, whether it's voice or data or something like this. So the S flag here is the window size, exactly similar to TCP, except that when the S flag is 1, what does that mean? For TCP, what does that mean if the window size is 1? Eh? If the window size is 1, there is a special name for flow control when the window size is 1. This is called what? When TCP provides flow control and reliability. Okay? So there is the window technique, right? So at the beginning we studied the simple case when the window size is 1. And then we discussed the case when the window size is more than 1, in which case we studied the different cases for sliding, how we slide the window, and based on the acknowledgement and so on and so forth, right? And we said that the number of sequences is always the window size plus 1. So here we have either 0 or 1. So we have 0 and 1 as sequences. So the window size is 1. So this is called a stop and wait. Stop and wait. So stop and wait, this means that you send only one segment and you don't send any other segment before you get the acknowledgement. When the window size is more than 1, then you send multiple segments. And then when the window finishes, then and only then you wait for acknowledgement. So this means here that we use stop and wait. Stop and wait, they call stop and wait ARQ, automatic repeat request, which means that you send one frame. Of course, here we call it frame, not segment. We send one frame, and then we have to wait for the acknowledgement. Okay? When we get the acknowledgement, then and only then we can send another one. And pay attention to the fact that when we send a frame, we have to wait for the acknowledgement on another time slot. Okay? So this is the stop and wait ARQ. So, and that's why actually, because the window size is 1, we are trying to increase the efficiency using the different slots, the different slot frame. So if you, because the stop and wait is kind of restrictive because you have to send one frame only and then wait for the acknowledgement. And that can actually have a very low utilization in terms of the communication channel. So you can increase that utilization by enlarging the frame into 3 slots or 5 slots. So this way it's as if you have tripled the window size or multiplied the window size by 5. It's as if you have sent 5 frames and then you wait for acknowledgement. Which is smart actually, because that's what TCP does. It sends 1 segment, 2 segments, 3 segments. So they here, we might as well send them all at the same time. But the trade-off is that the hopping frequency will drop when you, because 1 frame has to be sent using only 1 frequency. But then we said that the hopping is, why the hopping is required? To deal with the interference between the different piconets. So within one piconet, we use 1 frequency, right? So there is no intra-piconet interference. That's not there. But we're hopping to just control the interference between 2 piconets or more. Okay? All right, so any question here? Clear? All right, so now there are these 2 types of connections, or maybe you can stop here just to have some time to